And there's a third nice thing. Oh, your question go on.
Just relating to the correspondence between the 3D space and the inner space. What CFT theory corresponds to the particle Hawking state, and what special property do they have? I mean, that theory have, that CFT theory.
So correct. So that is actually the fourth point. So the Hartley-Hawking state does look like one of these theory partition functions. And okay, I have intuition only up to 2 points. So if you actually extrapolate the 2-point correlation in decision, the dual to that 2-point dual meaning basically you have a 2-point correlator. You just flip the delta, make it t minus delta, and that 2-point correlator is the 2-point correlator in the dual CFT. So I guess Hartley-Hawking state is the only state where the dual CFT has information about your bulk theory in decision. Because the wave function coefficients of Hartley-Hawking state, they have information about the bulk interactions.
But it's supposed to be some particular theory, is it?
The CFT is supposed to be a particular theory.
Yeah, the dual to Hartley-Hawking state
Right.
is a particular CFT.
Look, we use the term CFT to relate to reservation. So by CFT, we just mean a family of endpoint functions. We don't mean anything more than that. We're not saying there's a spectrum or a symmetry or anything. So okay, in that sense, the particular CFT don't mean that negative sense. We're not claiming anything more than that. There are explicit constructions of CFTs which give things like this. Like there is a paper 2017 by Dionysios Animos, and he constructs a CFT from an ON model. But there are very few explicit constructions like this. In general, it's hard to construct.
Yeah, perhaps to clarify, I think if you have a different bulk theory, correlation functions in Hartley-Hawking state could be different.
Right.
So in some sense, different bulk theories correspond to
Different,
even in the Hartley-Hawking state.
Correct.
They correspond to different spectrum.
That's true.
And endpoint functions.
Yeah,
It will depend on the details of the bulk theory.
Right.
So these fields.
Correct. So the particular construction that we're going to use in this thesis is what's called the small fluctuation basis. The small fluctuation basis is basically the following construction. I won't go into the explicit constructions of the thesis, but I'll just explain with this picture here. So imagine you have this solution space, which is the entire square, and you have a dot in that solution space, which is the Hartley-Hawking state. Then you can make convex combinations of the wave function coefficients. Convex combination just means taking the unit combination of the coefficients at 1. You can take a convex combination of the coefficients with a different theory. So let's say that G1 is a different theory, and it's also a state in the solution space. It may or may not be a space in the Hilbert space. It may be normalizable, non-normalizable, who knows. But let's say it's a state which is a wave function which looks like the e to the I dash times z. Then, if you take a convex combination with the parameter lambda, then you can interpolate a curve between these two states, Hartley-Hawking and this modified state. Then this tangent vector, because it's almost like a difference between these two neighboring states here and the neighboring state in the interpolation curve here, that state also is a state in the solution space. And we propose that these states actually form a meaningful Hilbert space. So of course I'm not talking about just one tangent state, but I'm talking about all different types of tangent state, all pivoting on the Hartley-Hawking state. So these states look like the following. They have this delta G tail that is acting on the Hartley-Hawking state. In the Ket notation, they just look like excitations. But one thing to be careful about here is that these excitations in the naive QFT norm are not normalizable. So these G's, remember, are CFT endpoint functions, which means that they don't have compact supported imposition. They can just keep going on forever. So if you just took psi norm in the QFT sense, then this number is going to necessarily diverge. It's never going to be convergent. So naively, this type of thing, this never works. So what's the solution to this? The solution is a novel non-proposal. Yeah. It's a novel non-proposal. But why do we need a norm? We need a norm because we want to do quantum mechanics, and we need a Hilbert space for that. And in the definition of a Hilbert space, it says that it's a complex inner product space. Inner product space means a space which has inner product structure on it. But we'll just define a norm, and inner product for a complex linear space is the same as norm. if you know all the norms in the complex linear space, you know all the inner products as well. So we will not make the distinction. We just offer a procedure for finding the norm. One nice thing is that in our proposal for the norm structure, we will get a natural way of defining cosmological correlators as well, which we believe is an improvement over the way that cosmological correlators are defined in existing literature. So what's the prescription? The prescription is the following. I'll remind you what the state looks like. The state looks like psi equals a bunch of excitations. So curly G means the excitation functional coefficient times field insertions times e to the is times z. E to the is, of course, is the number. So norm is the following. You just take psi square. That this whole thing starting from kappa del g z square, this is just psi square. And you integrate that over all the spatial configurations of geometry and all the spatial configurations of the quantity. But one has to divide this by an infinite number, and I'll come to why that is the case. But first I'll just say that this proposal also gives you a prescription for finding an expectation value of an operator which is also different by invariant. The proposal, as you must have guessed, is just inserting the different by invariant operator A inside the functional integral. But why is this division by volume of diff cross volume group? That's a group, by the way. Diff cross volume means the group which is made by diffeomorphism and Y symmetry. This is the following: that you see the wave function has a diff cross Y invariance. So if I integrate over all geometries, then there are these things called gauge orbits. Gauge orbits are gauge orbits are subspaces of configuration space over which the wave function does not change at all. So that means that within this integral, there are a few of these integrals, which is like integrating 1 over all real numbers. That number obviously is divergent because the diff cross Y group is not a compact group like SU2 or U1. It's a non-compact group that has infinite volume. So the number in the integral obviously is divergent, and that has to be divided therefore by the diff cross Y group. So the solution is actually implemented in the following way. Again, this is rhyming to what we do in string theory, is by fixing gauge. So we want to fix the trace of our gravitational fluctuations, of the gravitational field itself, and we would also like it to be transverse. This is called TT gauge, traceless transverse. If one does that, by inserting these delta functions in the path integral, in the functional integral, then one incurs what is called the Fourier-Popov determinant. Those are the red terms in this, in the first point. And that determinant ensures that different choices of gauge give you the same number. You say I could have fixed gauge as TT, but I could have had other gauges as well. Some other gauge. GI equal to 2T instead of T. And I would expect this norm to be very much of a choice. And that's what this Fourier-Popov determinant ensures. Functionally, what this is integrating over also what's called a ghost action. The ghost action is two fermionic fields, C and C bar, and they interact with just the gravitational field. And this ensures the image invariance of this norm. But there is a further problem here. The problem is the following: that in the large group of diffeomorphism and Y, there is a very small subgroup which preserves the gauge conditions that we have set. And those diffeomorphisms are translations, rotations, dilatations, and with special conformal transformations, but with one correction, which depends on the gravitational fluctuation itself. This is actually the conformal group. But the commutation relation between these vector fields is slightly modified depending on the background, but it still forms the conformal group. The special conformal transformation gets a correction which depends on H because, first I will say that this correction does not exist if my H is 0. So if I have a perfectly spherical visitor slice, then I have the perfect conformal group. There are no corrections. But the moment there is a correction in the geometry, my special conformal transformations, they receive a correction. And this is going to mean something at the end when I discuss a lot of information. So the problem here is that this group, again, the conformal group, is not compact. It has infinite volume. Therefore, in the integral, there is going to be one factor of this divergence. So even though we have fixed gauge, we have still not gotten rid of all of the divergence in our functional intent. So what's the solution? The solution is the following. Again, consider the state, which looks like a tail on top of the Hartley-Hawking vacuum, and fix 3 points in the integral. So what do you mean by fixing 3 points? It means that look, I have these functionals which are actually integrals over all of space. There's a g of y times h of y integrated over all of y. Vectorization just means 1 to n. And in principle, so I'm integrating a lot of these points, and in principle, I could fix 3 of these points to absorb one factor of the conformal group volume by inserting these delta functions, which further incurs me a Faddeev determinant, but we won't worry so much about it. So the extra determinant is just some post insertions. And this actually solves the problem. This actually brings out one factor of the conformal group volume, and once you divide by that, it gives you a finite number. This thing in a very limited context, this whole process in a very limited context, was already understood by Higuchi in 1991. So the context was massless scalar inviscid 2. We have generalized that, but I'll just revise what he understood in 1991. He understood the following: that gravitational constraints in the non-gravitational limit give you visitor in variant states, meaning states which are annihilated by de Sitter symmetry operations called U. And of course, de Sitter symmetry group, as you all know, forms the conformal group as well, SO1, T plus 1. But this meant that all of these states were actually group sum versions of seed states. Seed states meaning there's some other chaotic state. Every state which is a discrete variant state is necessarily a group sum version of some other state. And therefore the norm just diverged. The QFT norm diverged. He found the same thing. And his proposal was divide the naive QFT norm by a volume of the conformal group, and he showed that this is actually finite. And he found a orthonormal basis for such states. We find that our procedure, when you reduce it down to the non-gravitational limit, setting Newton constant to 0, gives you precisely Higuchi's inner product multiplied by some trivial factor, which is finite. This is SOD minus 1, which is a compact group. So that's just a finite DC number. So while it is true that our non-proposal, we could have inserted more different invariant integrals, insertions in our integral, and of course our non-proposal is not unique by any stretch of the imagination. There is one validation that it does reduce down to Higuchi's norm.
Can I ask?
Sure.
So the way you get to the SO1 comma T plus 1 in your formalism is because you are doing some gauge fixing and then there is some residual gauge symmetry. Right? So there you haven't said anything about isometries as such.
I have. The isometries are the residual gauge.
Like if you did some other gauge fixing, would you still get the same?
Oh, it wouldn't be as simple looking, but it would.
But you're saying it will still be SO T plus 1 comma 1.
I believe so. Yes.
Volume should not change. I mean, in the end, the answer should not change.
Yeah, right. That's correct. But okay, all of these are nice things to say at a formal level. I expect that to happen, but I haven't checked with other. Okay, we have in the thesis we have checked with spherical gauge fixing as well. But okay, we have checked those two examples, and there is
Different gauge fixing, zero nodes and all these things.
yeah, that will be different, but it's
For
still
example,
the
in
same.
string theory,
Yeah.
if you do light work, you couldn't get any C.
Okay, that's a good point, but it's true that in string theory different gauges you get slightly different things. But here we have done two gauge fixings. One is this TT gauge in the flat coordinates, but we have also done a TT equivalent in spherical coordinates, and it gives the same structure of norms. But this could be incidental. I agree that in a different gauge fixing.
That's because we won't have the same same number of Killing isometries. Some sense.
That makes sense.
But in some other case, if you that's what happens in string theory also.
I
The
see.
dipole kind of
So
makes-
this is like the point that we need 3 insertions in a sphere, right? This is not a question of like AU or in any elements. So these 0 mode insertions you would always need, right? Whatever
But is it not true, Subrat, that the residual gauge might vary depending on what gauge you choose? Like instinctively you choose conformal gauge. Therefore you need this insertion or whatever, you get the conformal gauge.
Of course, the form of the modes would vary, I think. I don't think that I don't think that the algebra would vary. That would be very strange.
The final answer should be the same. But but how that answer comes
Of
about.
course, but the form that is the S1 B plus 1 redundancy. You would ask the same question in string theory, right? Let's say I fix gauge in some other way. Can I somehow get away with only one insertion on the sphere?
Oh, I see.
The answer is no, right? Like you can't define a one-point function just by fixing gauge in some clever way.
Yeah, that is true, but you might not have any C code, so that may come because of some other constraints.
That's possible. It's possible that
Also, my question was more about the group itself. Like, is the SO T plus 1, incidental, or like you have to have something like this because of this isometry that remains even if you take the kappa to 0?
Yeah, I believe it's not incidental. I believe it's not incidental because no matter what norm you propose, it has to reduce to this the QFT norm. So I believe it's not incidental. This would be actually a check of any sensible norm.
Yeah, so in the what's string theory one on does a similar covariant gauge fixing. There is norm problem is just that fact that the host number is not conserved. And that is a specific violation, right? And you don't have to do really anything extra, right? Once you understand that, then everything falls out.
True. But there the discussion is about evaluating a partition function. Here it's about a norm. So there the norms are all.
So norm is correlation function, right? Correlation function contains norm information also.
Okay. True. Okay, fine. Yeah, true.
And the point you know that you have to insert 3 rows to get a non-zero correlation function.
That's correct.
3 plus 3.
That's correct.
And after that, you don't have to do anything extra like group averaging extra. It happens automatically, right? So Canton reformulate this in that language that once you introduce the variable host, just look at the host number anomaly and then.
Oh no, but it's already like that. So once you have inserted the ghost insertions, you're not doing any group averaging. I'm saying that the group averaging procedure, which is done without all of this knowledge, this agrees with it. That's all I'm saying. So there was a very naive calculation done long time ago, which they didn't know of normal. So so Higuchi's prescription was a little bit ad hoc. It was not super well justified, but I guess our norm serves as justification. So we didn't do any group averaging. This naturally falls out of the prescription, just like string theory.
You showed the expression with the funny pop-up determinant solver. Right?
Yeah, that's this.
Yeah, so maybe somewhere there should be some ghost in the Ashok actually said ghost institutions here, right?
Yeah, that's ghost.
CI1, CI till infinity.
Yeah, but in string theory, you don't use it to define norm. You simply say that the correlation function should have this whole
same here. So let's say if you want to define a correlation function also, we would put some insertions, and you would see that unless you inserted at least 3 of these ghosts, you would get 0.
Yeah, but I'm saying there is no natural definition of norm in string theory, precisely because of this. Right? You calculate the inner product between states of different host number.
That's true. That's right.
So why do you need the norm in the first place? One does your what is string theory without defining the norm, right? Just in terms of correlation functions. Or inner product matrix. Inner product matrix you have total host number adding up to 6 or 1, right?
Correct.
So can one do something similar instead of then you want to define norm?
Okay, I'm not sure how to think about it, but here naively we just thought that okay, you should define a norm because you would eventually, you're doing QFT, right? You would eventually want to divide by the norm if you have expectations. So that was a motivation, but okay, I'll have to think about that stuff.
Ashok, to define the Hilbert space structure, wouldn't it be important for us to define a norm with like positive definiteness?
Okay, in the word string theory, you don't emphasize on positive definiteness because there are these various gauge conditions. At the end, of course, everything, the physical quantities become positive definite.
The
right? But at the intermediate stage,
and so you're right. It's rarely computing an S matrix, and it's very mysterious why in the end the space-time S matrix turns out to have the right properties. But here, in some sense, aren't we computing something? I mean, it's more straightforward. Right? We're directly computing the norm of a wave function, and so I'm a little confused about.
I mean, what you need is the matrix element, right, between the wave function. Matrix element of some set of operators between the wave function, not require the norm, right?
And this is true. I agree that what we really need is a matrix element or some set of operators between the two. And you're right. So we could phrase things you're saying in that language rather than.
Yeah, rather than the
What
norm.
would be the advantage, though?
Pardon?
What would be the advantage, sir? It would be a more covariant spacing.
Yeah, I mean that seems more natural. Here the norm really doesn't exist and you are trying to force it. Right? But you think in terms of the matrix element, you just have to say that whatever operator you are using to calculate the matrix element has to have certain host number.
Right. Okay, that's possible.
Perhaps
Physically, it could seem a little unnatural to not have a norm on the Hilbert space, but maybe one could frame things in only in terms of observables and say they have. That's possible.
Yeah, perhaps the point is that here you're choosing 3 points, and then like the 3 points are natural to choose if there are actually physical operators there. Then choosing them. Maybe that's
The 3 points are not going to affect anything.
Yeah, it's not going to affect anything, but this choice is can be made physical by actually putting operators at the points that you're choosing.
This is true that if you put operators, it could be physical.
I think that's what we do often in string theory, that we actually have a fixed vertex operators, integrated vertex operators, and then we just fix them to a 0. But
yeah, you could say we should never speak of norm and only speak of observer.
Moving on. Now there's one more issue. Whoever has worked in this here must have heard of alpha. Alpha vacua are a 2-parameter family of vacua which are drawn here. I've never seen this cartoon anywhere, but the way that it's presented by the people who discovered it, which is Bruce Allen and Ray Ghotubabu in 1985, they basically proposed a 2-parameter family of vacua in Decider field theory, which looks like this. So it's a hyperboloid, and each point in this hyperboloid is one vacuum. It's a different bunch of states which all have symmetries which I'll explain in a moment. And the Euclidean vacuum or the bunch Davies is basically the tip. I don't know if it's visible so well. That's the tip of this hyperboloid. And the property is that all of these vacua are SO plus 1, comma D plus 1 invariant, meaning they're invariant under the identity component of the Decider group. There's a subfamily of these vacua which is called the alpha vacua, and they are invariant under a slightly larger group, which is the entirety of the Decider symmetry group, which is O1, comma D plus 1. And then a natural question arises that, okay, we have this Hilbert space. Do these alpha vacua, which are also symmetric and which are also Decider invariant, just like the states that we proposed, just like the states that we talked about in the small fluctuation basis. So natural question arises that are these alpha beta vacua existent within this small fluctuation basis? And the answer that I have as of now is no, because one can show explicitly that these alpha beta vacua have infinite particles in the bunch Davies. They have an infinite bunch Davies number of particles. But the states that we just talked about in the small fluctuation basis have a finite number of particles. They can be thought of as finite number of particle excitations on bunch Davies and then averaged over the Decider group. But all of this averaging over the Decider group does not change particle number. So we say that the alpha beta vacua do not exist in the small fluctuation basis. One could ask whether alpha beta vacua are within the solution space of the form that we just said into the highest times z, and the answer for that I have is most probably yes, because in this paper by Sachin Jain and Niloy and collaborators, they have shown up to the 3rd order wave function coefficients that the wave function of alpha beta vacua look exactly like the highest times z, the type that we have here, just like Hartley-Hawking. So the answer to that question is probably yes. So coming to cosmological correlatives.
Perhaps if you could stop here and ask whether there are any questions.
I ask? So when you say that these alpha beta vacuola have infinite particles, you mean like some expectation value of some number?
Yeah, exactly. But just some A dagger wave that goes. If you just count the expectation value of A dagger wave, sum it out for all modes, you find that it's an infinite number of particles.
But you should really do it like if there are infinite number of modes, you mean like per mode or something?
Yeah, once you sum it up. So okay, yeah. So per mode it's finite number.
But then that's not really a issue.
So
Like, if there are infinite number of modes, then obviously you get infinite. But per mode, it's like a harmonic oscillator. Like for example, if you had like a, I don't know, if you had a coherent state, similar.
coherent state has finite norm, but okay, I'm not sure. Does coherent state have infinite particles in a harmonic oscillator? I can't remember off the bat, but
in a single harmonic oscillator, if you take the expectation value of n, it's probably not infinite.
probably a finite number.
But then you're summing over like infinitely many modes, right?
Exactly.
So there's some number for each mode,
Yeah.
and there are infinitely many. So, but that's not quite.
That's what particle number means, right? You have to take the state and then sum over all the modes.
No, what I'm saying is that does this preclusion incurred? Okay, are you like not including things like coherent states when you say something like this?
Am I not including things like coherent? But I'm not sure if what you're asking is do these alpha beta vacuola look like coherent states? I would say they do because the explicit form in some cases are norms, so they do look like coherent states. And it's true that per mode the number is finite. Per mode, if you just look at it that that's a finite number. But number of particles is defined as sum over all the modes. You would,
No, that's fine. But if something like a coherent state, you should not say that it's unphysical, right?
Oh, I'm not saying it's unphysical. I'm just saying it does not exist in the small fluctuation basis, in the Hilbert space. But okay, I see that also, I'm saying that they are unphysical. The thing is, they are unphysical for one more reason. Is that all of these alpha beta vacuola, except the blob at the end, which bunch of these, they have a slightly strange singularity structure as well. So all of these vacuola which are not the Euclidean vacuum have a singularity in the 2-point function. The 2-point function is an antipodal indices. So they have a slightly funny interpretation. It's not exactly like so they do not exactly create a Hadamard singularity. So that's not the only reason why I would say that are physical for other reasons, but maybe not an MTV disorder. Maybe they have interesting interpretations. Yes, I'm not sure.
Yeah. Any other questions?
Physically, I would think that since you look at late time, the alpha vacuum will look like that, right? Because even if you start with large energy density, you will just get iron.
Yeah, but okay, but this is divergent. Right? The energy density is it's an infinite number of particles. So I'm not.
But at late time, I would think it will become completely diamond, right? I
cannot say
if you try to evolve it backwards, probably you have to run into problems, right? At some point,
True.
you will see infinite density, but at late time, it shouldn't cause problem.
True, but then there's this conflict that they do look like infinite particles. I don't know what to do about that. They do look like infinite particles, but
Yeah, infinite particles and spread over infinite volume, right? Because
I think this might be the same issue we were discussing yesterday, which is that the correlators we are measuring are spread out over the celestial sphere. So we are also allowed to measure correlation functions from the North Pole to the South Pole at infinity.
yeah, true.
that's okay.
So those, locally, what you're saying is locally that they would look like that.
Okay. Yeah.
But and I think then we would see these strong similarities.
Sorry, what does that solve? I don't understand. Did you understand? What does that solve?
Well, I think that's what Subrata said. That's the reason why you are seeing these singularities.
Okay.
But even though locally that doesn't seem to be any problem.
I see.
Because locally it's infinity diamond, right? Because you are really looking at very large scale project.
Okay, maybe I can answer it. Okay, any more questions? Okay, so the last section which has maths in it. So what are cosmological correlators? Cosmological correlators are, like I said, the QFT handle that we have on the inflation situation. So they're usually defined in cosmological correlators literature as these endpoint functions in the Hartle-Hawking state. To probe any system, our first handle is always these endpoint functions. But the special thing about these is because we can only see the cosmic microwave background at one particular time, which is when the things became opaque, or when the thing was last opaque. So all of these correlators are equal time correlators. That's really the only thing that we can see. And as of now, there's no way of knowing what these correlators look like, where the time argument of one of these insertions is up or down from the rest. So that's the object that we're interested in. But one issue with defining such a thing is that there are no local fields which are gauge invariant in gravity. And a very simple example of this is we take a scalar field, and if we just do a gauge transformation in gravity, which is a diffeomorphism, then that scalar field transforms as phi goes to phi plus xi I del I phi, where xi is the diffeomorphism. That's true for Riemann curvature, Ricci curvature. Every single thing in gravity transforms under diffeomorphism, and it's impossible to make local gauge invariants. So, nevertheless, these insertions we propose can be thought of as gauge fixed gauge invariants. So the meaning is slightly subtle, and I'll unpack this. The meaning is the following: that there exist gauge invariants in this theory, of course, those are the observables, but they don't take any local form. However, within a fixed gauge, when you input some gauge fixing data, then that non-local form can reduce down to a local bunch of insertions. We have an explicit formal proof of this fact in the non-gravitational limit. And in our upcoming paper, we also have an explicit construction of how to make gauge invariants from local insertions in the non-gravitational limit. We expect that for non-zero Newton's constant, this is a much harder task, which is why we just stuck to the non-gravitational limit. But in principle, we believe this is true. Believing this, we can define cosmological correlators in the following way. You just take a string of operators, and you insert that within the functional integral prescription that we have, but now without any point fixing. So now we are assuming, in fact, now the point is that all of the gauge fixing in the path integral has already been done by fixing the points in this gauge invariant. So there is no residual gauge fixing anymore because that's already been done by fixing the points in this C. And that's a definition for the cosmological correlator. And now one must know. So okay, so I have used some connex notation here. That's e to the minus calligraphic s, and that contains the wave function square, the ghost action, and all of that. And all of those things. Okay, so I've just written. Sorry, there's one point. I've just written it. So
Some of ING has to be 3. Some of I plus j.
That's true. Yeah. So correct. So this psi looks like n particle insertion. So 2n plus p plus q has to be larger than 3. That's what we define there.
So, can you think about what is this from the point of view of BRC? You are looking at, so usually what we say is that the physical states are BRC groups, and there is not the BRC that. And we want the operators also to be BRC. Right. Okay, so now are you thinking about, so what are you doing here? Are you kind of leaving the first condition, second condition, both conditions? You're talking some BRC close conditions? Is that
No, so BRC, so operators with BRC close are actually gauge invariants, right?
Yeah.
But they're
Kind
gauge.
of, but there's a more precise way of saying it's BRC close. Because this is after gauge fixing. Right? We talk about BRC after gauge fixing. So we talk about gauge invariant, but we talk about BRC
I see.
after gauge fixing.
I see.
And then we talk about BRC close. So is it like your states are not BRC close? Is it like your operators are not BRC close? What are you doing?
I see. Okay, that's a good question. I'm not so sure. I'm sure it can be put there. Like Witten has done something which where he has framed pretty much what we have done in the BRC language. I think there is an interpretation, but I cannot reproduce it.
Okay, I'll ask one quick question. So the reason you kept that point fixed and so on was that there was an infinity.
Correct.
you're saying this thing that you've written down doesn't have that inclusion?
Yeah, it doesn't, because there's more than 3 points fixed already inside the entire list.
So you are doing a point fix. So I'm confused by the statement that there's no point fix.
Oh, so there's no point fixing anymore by hand. I don't need to insert delta functions or anything. I'm saying that it's already been done for us by the choice of the form of the insertion.
So okay, so you do point fixing, but you're using the the operators to do that, like what we do in string theory. But you're not including the ghost correlation.
That has to the ghost insertions have to be inserted as well. I'm sorry, I've not integrated this here, but the ghost insertions should be there as well.
Okay, so then this is the same as
No, so the ghost insertion. Sorry, I'll just say that they're already there. They're already there in the scheme of minus S. I believe you can just continue to choose those ghost insertions as any.
there is a ghost action.
There's a ghost action.
But I'm talking about you have this the triple ghost insertion expectation value that is there.
That's